Hello EMF, my name is Ben, I'm a spacecraft electronics engineer down in Harwell. Before we get really going, is this gonna, there we go. So this is my project from the EMF this weekend. This picture is part of my installation, the EMF Sky Survey, and this was taken purely on Thursday night. So if you want to hear anything about this, then come and see me at Test Village and we can show you the telescope that took it. But I'm going to talk mostly about actual telescopes today. So my talk is kind of in three general themes. I'm going to go through some infrared telescopes and talk a bit about what general types of instruments you might find on a space telescope. Then we'll go and get a bit narrower and we'll talk about the SLSTR mission and the full climate program that goes around looking at surface temperature measurements. That's been going on since about the 1980s and that's primarily what I'm working on at the moment. And then finally we'll look a bit about calibration. So space telescopes have very accurate calibration, but their calibration doesn't last. So we'll talk a bit about why recalibration is so important in space and the hardware that lets us do that. So I have to start with a disclaimer. This is going to try to be a non-technical talk. However, it's an extremely technical subject, so I'm going to try and get it down the middle. And if there's any really detailed technical information in the slides, you kind of don't need to understand it to get the point. So hopefully I keep it in an easier to understand framing. There are also going to be lots of pictures of flight hardware. If you've never seen space telescope flight hardware, that's quite cool. So, next slide. If you make it to the end, I have a high definition recording of this launch. This is the NG-11 Antares rocket flying from Wallops Air Force Base. This was in 2019, and I was lucky enough to go there with the NASA social program. And I got a very high definition recording of that launch, so at the end I will play that through hopefully some very nice speakers, and it will get close to what it feels like to have been there in person. So who am I? I mostly work on sensor front-end electronics, so that's the big box of electronics that primarily drives the actual silicon sensor on space telescope cameras. Mostly I work on climate missions, but also heliophysics missions. So most recently, NASA's Punch mission flying for small spacecraft to monitor the solar coronosphere, and then also a company called Spire flying a new type of instrument looking at more accurate weather observations on Earth. So you can see some flight hardware here. That box at the top, that's the instrument box for the Punch mission on the NASA Punch mission. So that's got 4 PCB cards in, and it's probably about this sort of size. And then at the bottom here, this is the prototype for the HIMSS CubeSat mission, which has got a microwave sounder on it. And our little box of electronics is that little gold box there. And I work for RALSpace. RALSpace are a public-funded body. We're basically a government arm's-length body. We are the UK's National Space Laboratory. If you're at all familiar with NASA Goddard, you might kind of draw some parallels to what our role is in the UK's science sector and how we design instrumentation or test facilities for industry and other space agencies. So I'm going to start generally. So hopefully you all know what this telescope is. If you don't, I don't know why you're in this talk. This is the James Webb Space Telescope. It's got 4 instruments on it. This one is generally pitched as being an American mission. It's in fact not. It's probably the most international space telescope ever launched. MIRI in particular, the mid-infrared instrument, was led by a UK consortium with contributions from Europe. And at least one of the other instruments has a pretty significant European contribution too, and another one has quite a big Canadian influence too. So although the Americans built most of the spacecraft bus itself with all the mirrors and optics, the actual instrumentation inside is very, very international. So there's a few types of instruments on board. Most of these types are kind of in each of the 4 instruments, but they have various different functions and modes and different types of spectrum they look at. First one's quite obvious. You probably all know what cameras do. It's a 2-dimensional array of pixels. It takes values from those pixels and those become an image. Spectrographs are a little bit different. They break the light down into the spectrum and take more of a 1-dimensional measurement. So you can see the components of that light frequency instead of the amounts in different places. And then finally, the other common one on the Webb Space Telescope is a coronagraph. That is basically the front stage of the camera optics that blocks starlight. So you can see planets or other faint objects nearby without the starlight blowing out the image. So this is some flight pictures of MIRI. This was when it was being tested at RAL Space down in Harwell. So you can see at the top there, this is it going into the thermal vacuum chamber for testing. That one there is the actual flight unit. I think this one here is also the actual flight unit undergoing alignment testing and field of view testing. And then the graphic over here kind of gives you an idea of what the field of view of that is and the types of instrumentation inside MIRI. And if you saw the Laura from Space Talk yesterday, I think it was, then you would probably have seen quite a lot of pictures of our test facilities, which part of this comes from. So this is kind of an example of what comes from MIRI. This is a Wolf Rayet star. It's surrounded by quite a lot of radiation and dust. It's 4 light years across. It's 8,000 light years away. And to give you an example of how difficult this image is to take, this instrument is currently cooled down to 6.7 Kelvin. So that's minus 266 degrees C. And if you don't do that, then the latent heat in the detector makes this image basically impossible to capture. So you have to get down right to the limit of literal physics to be able to take these kinds of infrared pictures. To give you an idea about the accuracy and how accurate these instruments are, this green blob is the most distant object ever taken in an image. It's a galaxy called MOM Z17. It was discovered last year, and the redshift, if there's any astrophysicists in the room, is quite extreme. A 14.4 redshift figure basically means you look at the wavelength of the light when it was transmitted, and you multiply that by 15.4, and that becomes the wavelength when we see it. So that's quite extreme. The table here shows a bit about how far that light has traveled to a given Z figure. A Z of 10 means it's moved 13 billion years, pretty much, and a Z of 14 means it's moved 13.5 billion years, and that object is now 33.8 billion light years away. So these instruments have to be incredibly sensitive to be able to make these kinds of measurements to any level of accuracy, and I think that Z figure is accurate to within a couple of hundredths, so it's within maybe 100 million light years or so of distance. More specifically, and the instruments I'm going to be talking about for the rest of today are radiometers. So radiometers are kind of like cameras, except instead of looking at two-dimensional arrays of pixels, it's a bit more one-dimensional, and instead of looking at specific wavelengths, we kind of look at a big band of wavelengths. And then we want to very accurately measure the amount of radiation that's been emitted from from the object that we're looking at. So these are generally designed to be incredibly precise. And the reason we need them to be precise is because we need to do very accurate climate science and climate modeling with these measurements. So this one at the top here, I think, is one of the models for a mission called SLSTR. And there's some more flight images of that one there. This is all going into the thermal vacuum chambers over at RAL Space. So why do we need to take these really accurate measurements of these really specific bands? Well, we need to know how this works. This is the global mean sea surface temperature. And we have to have a very clear model of what these drivers are that are driving these rising temperatures. And the only way we can work out exactly what these drivers are doing is by incredibly accurate measurements of this sea surface temperature. And this graph will kind of show how all of these little factors contribute to the overall rising temperature. And the other reason why they have to be so accurate is they need to detect a 0.02 degrees Celsius rays per year. This is also from space. This is 700 kilometers away. And this is obviously a very small signal to try to detect. And the other problem is instruments tend to drift while they're in space. Their calibrations change. So this is a very difficult level of accuracy to get down to. So this all started in the 1980s. This was the long-track scanning radiometer. This was built in the UK with a consortium of British and Australian organizations. And basically this was the first detector ever designed to measure sea surface temperature specifically for climate change. There were 3 versions of this detector. One was flown in 1991 and the most latest one was flown in 2012. You can see there's 2 kind of banana-shaped apertures, which is where the main detection happens. On the right there, that's for calibration on the ground. And I also want to draw your attention to the 2 cylinders at the top and bottom. This is the black body calibration sources, and we're going to talk about those in a little bit. So very briefly about how this works. The two banana-shaped apertures form two sets of scanning channels. So we've got one that goes straight down and another one at an angle out in front. And that's used to do atmospheric corrections, so ensuring we get a very accurate ground measurement. So here's the three that launched. You can see there's some different, it's evolved over the three programs. They added a lot of capabilities to measure things like aerosols, land temperature, atmospheric temperature, cloud temperature over the three programs. So this was quite evolving quite quickly. This was over 20 years. This is the current gen. This is SLSTR on ESA's Sentinel-3 mission. You can kind of ignore all the technical detail, but this is the same kind of double banana aperture, and if in the middle you can kind of see the bucket covered in foil. That's the black body calibration system. So Sentinel-3 has flown twice so far. There's another one flying next month, I think, 2 months, and another one next year, most likely. And right now, as part of my day job, we are now working on the next gen. We have only just started designing flight hardware for the next gen. That will be flying in 2035. So this is the kind of data we expect to get out of this. This is from AATSR, which was the third one in that initial program. So this is the kind of sea surface temperature map that we're going to intend to get out of this mission. And we use that data to produce data sets like this, which give you trends for surface and air temperature. And these are the kind of models that we have to have incredibly high accuracy to get accurate models of climate change. So that's how we get to those measurements. How do we know that we can trust them? And that's the biggest issue in climate science, really, is consistently trusted measurements and models. We use reference thermometers. Everything you put into space will drift. So the resistance values will drift, the properties of the circuits will drift. This is all caused by radiation, temperature swings, reliability of components. You cannot have a calibrated mission that's been set up on the ground and expect it to work to the same accuracy for a 10-year mission duration. So we have lots of uncertainties being introduced. We have differences between the same instruments on different spacecraft, and we don't get any trust between these measurements unless we correct it. So this is the type of hardware we use to correct it. This is called a black body cavity. For reference of scale, it's about this big. It's probably about a football size. It's basically a big metal bucket. Inside that metal bucket is a layer of Vantablack or very similar coating. And the purpose of that is to produce a thermally ideal object. So this, inside this cavity, this will emit basically only infrared radiation. So from that, we can use the temperature of the top of the cavity to give us a very accurate calibration for our infrared optics. So we use all of these electronics around the side. There's probably about 10 or 12 thermometers on top of that cavity, and we produce incredibly accurate models of the temperature of that base with which to compare the measurements from the instrument, so that we know that our measurement is very accurately aligned to what the actual temperature of that bucket is. So that's that one. The next gen ones are on the order of 10 millikelvin temperature accuracy, so 0.01 of a degree. And yes, if anyone asks, that top one, that is a cylindrical PCB. It was an absolute nightmare to build, and we are not building them anymore. I have yet to see one, by the way, but it's very cool. The problem we have is, as mentioned before, all electronics in space will drift. Their properties will change. On the ground, we use incredibly accurate resistor bridges to kind of pre-calibrate these and get them set up. These bridges don't exist in space. It's not possible for them to exist in space. They would also drift with the rest of the instrument. So how do we calibrate the calibration electronics? We can't have calibration electronics all the way down. It doesn't work. It would all drift. So we have to do some quite tricky things to consistently produce measurements that we can trust through a 10 or even 15-year mission duration. The way we do it in the next gen is quite clever, and it involves phase change. So if you imagine phase changing, when you've got a solid that melts, the temperature of that material will rise, and that rises until it starts to melt, at which point it will stop rising until it's fully melted. So we use this property, and I've got a nice graph here. we use this property to have a fixed reference point for temperature that doesn't change when the space environment interferes with your electronics. So that's the temperature of the gallium inside our phase change cell. As that melts, that temperature will stop rising, and we use that as a very specific known reference point. So if you imagine we've got drift interfering with all our climate measurements, so red is the line of what would happen if we didn't correct this drift at an amount of 0.05 Celsius per year. From earlier, we saw that we need to be measuring 0.02 to have anything like an accurate measurement. So with these annual corrections through these phase change, we can get that down under 0.02, which is how we are now able to measure long-term, very accurate climate data. So this is some of the next-gen stuff. This on the left here was a model called Engineers, which was basically a massive rigid flex network instead of that horrendous cylindrical PCB. This one measures temperature much more accurately than the previous one did. It's much lighter. It's infinitely more easy to build. You can kind of see some pictures of it here. That one on the left, this red-based one is the SLSTR black body, and it's got a massive box of electronics next to it. This one is the Engineers one, and all the electronics are inside this cavity area on the left here. And you can kind of see at the top, that little bolt-looking thing is a little phase change cell. It's about this big. There's about 0.5 gram of gallium in there, and that's what we use as a reference point to consistently recalibrate the calibration system. This is semi-flying at the moment. It's flown on the HIMSS mission, which I mentioned earlier. That's a CubeSat testing out this technology before they fly it on a constellation. And right now, we are using this technology on the new generation of Sentinel-3 missions, which will be flying on the next ESA program in 2034, 2035. So that is, I think, it. But I do have a rocket launch for those of you who made it to the end. So, as promised, this was from 2019, and hopefully this goes through okay.
5, 4, 3, 2, 1. And we have engine ignition. We have liftoff. Series NG-11 mission to the ISS. Engine full power. At 2.
I don't know if you could feel the rumble, but I can up here. That's quite like what it is in real life. And they're going to, I think there's a set on Sunday evening who's going to play this in null sector. So if you want to hear it in really big bassy speakers, then you might actually feel the bone shaking in the null sector speakers. So yeah, that is me.